Okay, let's discuss problem number 9 on assignment 1. So, in assignment 1, the problem number 9 is given in this manner, like there is an axial element, and that axial element is subjected to a distributed force. Okay, and that distributed force, how the distributed force is varying, it's given as a function of x. Okay, it's not a uniformly distributed, it's a position varying, a spatial varying load. Okay, so now this is the load, and the question is you need to identify the displacement, which is u of x. Okay, the displacement means each and every point how it's been displaced. Okay, this particular point will be displaced to somewhere here, and how much it's been displaced is what u represents. Okay, and we need to come up with a function so that if I substitute u, maybe this point or this point, whatever, okay, where the x measures from this axis. Okay, and for that particular x, u will be given using this function. Okay, and how to identify that function, the displacement function, is the question. Okay, but in order to construct the displacement, we need to come up with the differential equation, and by solving the differential equation we can identify what is the u of x. Okay, so the solving part could be either analytical or a numerical using finite difference method. Okay, so first let's see what is the differential equation which we are trying to solve. So for that, what we are going to do is I'm going to take an infinite sample piece of element in this axial bar, and let me draw that infinite sample piece over here. Okay, and in that infinite sample piece, so where I am taking that infinite sample piece, this distance, okay, this distance is x and this is dx. Okay, so this little piece is what has been zoomed over here. Okay, so this is x and this is x plus dx. Okay, and in this infinite sample piece the forces are distributed. Okay, and which is like q of x. But what is the total force which has been applied on this infinite sample piece? That's q of x into dx, because the unit q of x is a force per length, and the total force on this infinite sample piece is force into length, right? So that's what q of x into dx. Fine. And I have sectioned this piece outside of the rest of the material, so that will so in that case I have to draw a free body diagram. Okay, because this part will provide a force on this element, and also this part will provide a force on this element. Okay, and that is the normal force. Okay, what is the normal force acting on this side? Let me call that normal force as n of x. I do not know that function, so I am just assuming it's n of x, and here it will be n of x plus dx. Okay, because it's at x plus dx. Okay, now let's apply the equilibrium equation. If we apply the equilibrium equation, what do we get? We will get n of x plus dx minus n of x equal to minus q of x, right? Okay, sorry, not q of x, q of x dx. Now take the dx downside, and if I do that, let me erase it and let me put it over here. I'll get it like this. And what's the left hand side? The left hand side is nothing but a derivative of n of x, right? So n prime of x, which is equal to minus q of x. Okay, so that's one equation, but not the final equation which we are going to solve. Okay, now n of x is a normal force, so n of x, which is equal to sigma of x into area A of x, provided A is varying as a function of x. Okay, so if I put that in this equation, what do I get? Let me erase these things. So sigma, or let me write A sigma, which is equal to minus q of x. Okay, so prime. So in the place of n, I have substitute sigma A. Okay, now we know the Hooke's law that sigma, which is equal to E into epsilon. I'm going to use that formula, and if I use that formula, what do I get? AE into epsilon whole prime is equal to minus q of x. And here once again, E could also be a function of x, okay, because at each and every section, say the material property is varying. So in that case, E could also be a function of x. In our case, this AE is given as a constant, and that constant is equal to 1. Okay, but anyway, let me just give you the general picture. Okay, so yeah, so AE epsilon is equal to epsilon the whole prime is equal to minus q of x. Now what we are going to do is we are going to come up with the relation between epsilon, which is a strain, and the displacement. Okay, so once again for that we will look into this infinite SML piece. Okay, so in this infinite SML piece, this position, this phase is moving to a certain distance, and that's u of x, where this section, which is at u of x plus dx, is moving some other distance, which is u of x plus dx. Okay, so in that case, what is the total change in length of that infinite SML piece? So that will be this displacement minus this displacement. Okay, so which means u of maybe I will write it over here, u of x plus dx minus u of x. Okay, and that's the change in length. Okay, what about the original length? The original length is this much, which is dx. Okay, divided by dx, and what is it? That's nothing but du dx. Okay, which is epsilon of x. So that's what, right? So change in length by original length is a strain. Okay, which is du by dx. And now we are going to substitute this relation in this equation. If I do that, what will I get? AE u prime the whole prime equal to minus q of x. Okay, and sometimes in most cases, at least for the problems which we dealt in academics, the a and e will be constant, and at that time I can remove this a and e outside of this bracket, so that ae u double prime, which is equal to minus q of x. Otherwise I'll put minus over here, which is equal to q of x. Okay, see, once again we have a second order differential equation, but it's in 1D, and the u is a function of x. Okay, so this is true only when a and e are constant. Okay, so this is the differential equation which you need to solve using finite difference method. One is using finite difference method and another one is using analytical method. Okay, and you need to compare the results for using both methods. Okay, thank you.